Hello, welcome back, everyone. My name is John Morrow. I am a professor of materials science and engineering at Penn State University. The topic of today's presentation is about the nature of the surroundings in thermodynamics. Now, when we study thermodynamics, we usually pay attention to the system because by definition, that is what we want to study. But the system is coupled to the surroundings, and there are some notions about what the surroundings entail out there in literature. And what I would like to do today is to give a critical eye to some of those assumptions and provide some general perspectives on the nature of the surroundings. There is a manuscript that accompanies this presentation. It has the same name, Nature of the Surroundings in Thermodynamics, and this was recently published in MRS Bulletin, the Materials Research Society Bulletin. The first author of this paper is my dear friend and colleague, Professor Longqing Chen from Penn State University. He is also author of this outstanding textbook, Thermodynamic Equilibrium and Stability of Materials. If you are looking for a really good textbook on thermodynamics that not only captures the essence of thermodynamics, but also is just beautifully written, be sure to get a copy of this book. I've got two copies, one at home and one here at the office. So let us dive into the topic of today's presentation. When we study thermodynamics, what we primarily care about is the system under study here, which has some internal energy associated with it, which is given by a capital U. The system is in contact with the surroundings. The surroundings have their own internal energy, U with a subscript SIR here. And together, the system and the surroundings are the universe. And so the total internal energy of the universe is the summation of the internal energy of the system and the internal energy of the surroundings. So U plus U surroundings gives us the total internal energy of the universe. And according to the first law of thermodynamics, the energy of the universe is a constant. So U total is a constant. Now, in thermodynamics, the term surroundings, also sometimes known as environment, is introduced when a system is first defined at the beginning of nearly every thermodynamics textbook. These surroundings are defined as the portion of the rest of the universe which directly interacts with the system. So what we're primarily interested in is the system. The system is in contact with the surroundings, and together they form the universe. Now, most of the time we pay attention to the system, but today we are going to focus on the surroundings. Now, first, I would like to start with some quotes from existing thermodynamics textbooks. This first quote comes from David Ragon's textbook, Thermodynamics of Materials. This is the textbook that I used as an undergraduate student a long time ago. And on page 49 of that book, Ragon writes, "The process of heat transfer at the boundaries of reservoirs 1 and 2, meaning the boundaries between the system and the surroundings, is considered to be reversible." So there is an assumption here in this book that the heat transfer process at this boundary between the system and the surroundings is reversible. Moving on to the next book, Thermodynamics of Solids by Swallen. A quote from page 27 in that book says, "Consider now the surroundings. As we pointed out, the irreversible process is able to transfer heat reversibly to the isothermal reservoir." So just like in Ragon, he's specifying that this is reversible heat transfer. And he's adding this additional assumption here that the reservoir, in other words, the surroundings, are isothermal. Now, the word reservoir here, it is meant to imply that the surroundings are very large compared to the system, and a byproduct of them being very large is that the temperature of the surroundings would be unaffected by transfer with the system. And so that's why he is considering here that the surroundings are an isothermal reservoir. Now, if we go to Callan's book, which is another excellent book, Callan writes in his second edition, page 106, a thermal reservoir is defined as a reversible heat source that is so large that any heat transfer of interest does not alter the temperature of the thermal reservoir. So very similar assumptions here about the reversibility of the heat transfer between the system and the surroundings, the assumption that the surroundings are very large compared to the system, and that any interaction between the system and the surroundings does not alter the temperature of the surroundings. And finally, let's consider the quote from Atkins' book on physical chemistry. This is probably the most popular textbook on physical chemistry, now in its 12th edition. And on page 79 of this 12th edition, Atkins writes, suppose that the surroundings consist of a large reservoir so that its volume does not change, no matter what happens in the much smaller system, provided the surroundings remain in internal equilibrium. So Atkins is going beyond saying that the surroundings need to be isothermal. He's also saying that the volume of the reservoir doesn't change. And this is also based on an assumption that the surroundings are very large. He's also assuming that the surroundings maintain internal equilibrium. So there are a lot of assumptions that various textbook authors have made, and a lot of assumptions out there in the general literature about what the surroundings need to entail. However, the objectives of this presentation and the objectives of our paper in MRS Bulletin are to demonstrate, first of all, that there's no need to assume that the surroundings are large. That is an unnecessary assumption. And in fact, it doesn't matter how large or how small the surroundings are. Secondly, there's no need to assume that processes involving the surroundings are reversible. And lastly, the system and the surroundings are in fact thermodynamically interchangeable. What I'm going to show is that it is completely arbitrary what you define as the system versus the surroundings. You can switch the two and end up with exactly the same equations. And so it doesn't matter what you define as the system versus the surroundings. It would just be a matter of convenience as to what it is that you want to study, and that would be defined as being the system. Moreover, since the surroundings do not need to be large, there's also no need to specify that the surroundings are isothermal or that they're constant volume. These factors don't matter in our thermodynamic treatment of the surroundings. Now, let's jump into some details here. First, a reminder that for a simple thermodynamic system, the internal energy of that system, U, has three contributions. The thermal energy, U sub T, the mechanical energy, U sub M, and the chemical energy, U sub C. And if you add these three contributions together, you get the total internal energy, U, of the system. Now, for each of these different types of energy, there are corresponding types of matter. So for a simple thermodynamic system, there are three basic variables representing the three types of matter. Those are, first of all, thermal matter, which is better known as entropy. That is given by the symbol S. Mechanical matter, or volume, which is given by the symbol V, and chemical matter, which is the number of moles of each of the chemical species. And that is given by the symbol capital N. In addition, we need to define three thermodynamic potentials for our simple system. A potential is just some amount of energy divided by its corresponding amount of matter. So, for example, the thermal potential is the amount of thermal energy divided by the amount of thermal matter. So this is the thermal contribution to the internal energy, U sub T, divided by the amount of thermal matter, which is the entropy. These are two extensive quantities, so both thermal energy and thermal matter would increase proportionally with the size of the system. And so what that means is if you divide the two, you get an intensive quantity instead of an extensive quantity. And this thermal potential is given by the symbol T, and this is simply temperature. So temperature is the thermal potential of the system. Moving on to mechanical potential, the mechanical potential is the mechanical energy divided by the amount of mechanical matter. So this is U sub m, the total amount of mechanical energy, divided by V, the volume of the system, which is the amount of mechanical matter. And this mechanical potential is better known as pressure, or more specifically, negative of the pressure, minus P, because of the way pressure is defined as being a compressive quantity instead of a tensile quantity. And then the third and final potential that we need to define today is the chemical potential. This is the amount of chemical energy divided by the amount of chemical matter, or in other words, U sub C divided by N, the number of moles, and that is simply mu, the chemical potential. Now, given these definitions of these three different potentials, we can write the total internal energy of the system U as follows. So U is equal to the summation of the thermal, mechanical, and chemical contributions to the internal energy, U sub T plus U sub M plus U sub C. Now, if we go up here to our equation for the thermal potential temperature, you see that the U sub T is simply T times S. It's the temperature multiplied by the entropy, and therefore we can replace U sub T with T times S. Now for U sub M, the mechanical energy, that is equal to negative pressure times volume. And so that becomes minus P times V. And the chemical energy becomes the chemical potential times N, the number of moles of our chemical matter. And so we can replace the U sub C with mu times N. And so this is why in thermodynamics, we typically see the internal energy of a system written as Ts minus PV plus mu times N, because those three terms are the thermal, mechanical, and chemical contributions to the internal energy. Now, chemical potential is directly related to the Gibbs free energy of the system. We have our equation here for internal energy, and we can rearrange these terms to bring the PV over to the left-hand side and the TS also over to the left-hand side. And what we get then is an equation for mu times N, which is equal to U plus PV minus TS. Now, these first two terms, U plus PV, you probably recognize as enthalpy, H. Enthalpy is defined as being the internal energy plus P times V. And if you look at this entire left-hand side of the equation overall, the enthalpy minus T times S, this is the Gibbs free energy. So what we have here on the left-hand side is the Gibbs free energy of the system, which is typically denoted with a capital G. And this is equal to the chemical energy of the system, U sub C. And that, of course, from the previous slide is equal to mu times N. And so just by moving the TS and the PV over to the left-hand side of the equation, you can see that mu times N here is equal to the Gibbs free energy of the system. And what that means is that the chemical potential is simply the Gibbs free energy divided by N, the number of moles of the species. Now, when we are concerned with the interactions between the system and the surroundings, what we can do is describe this in terms of an exchange of different types of energy between the system and its surroundings. In other words, suppose that we have the universe here where the system is on the left and the surroundings are on the right. The system has a temperature T, pressure P, and chemical potential mu sub I, where the subscript I is just accounting for the different types of chemical species in the system. So all three three of these potentials, temperature, pressure, and chemical potential, are defined for the system. These three potentials also need to be defined for the surroundings. So the surroundings needs to have its temperature, T surroundings, pressure, P surroundings, and chemical potentials, mu surroundings. These do not need to be the same as the system. They could be different. They could be the same. Either way is fine. But the way that we track the interactions that happen at this boundary between the system and the surroundings is to keep track of the amount of different types of matter that are exchanged. So, for example, we can have the exchange of thermal matter by which some amount of entropy enters the system from the surroundings. That is this dSE, where the superscript E just represents that it is entering the system. Likewise, we can have entropy entering the surrounding from the system, and that here is given as ds with the superscript surroundings. Likewise, there can be an exchange of mechanical matter, which means a volume exchange between the system and the surroundings. From the perspective of the system, the amount of volume entering the system is dV superscript E. The amount of volume entering the surroundings is dV superscript surroundings. And likewise, we can have an amount of exchange of chemical matter. Entering the system is dN with a superscript E, or entering the surroundings. And one thing to note, and I've got a separate video on this, so please check it out if you're interested. It's called First Law for Open Systems, is that if there is an exchange of chemical matter, that chemical matter can bring along entropy and volume with it. And that is covered in detail in that separate video on the first law of thermodynamics for open systems. So check that one out too if you are interested. Dr. Chen and I also have a paper specifically on that topic, also published in MRS Bulletin. But when you put all of this together, we can write an expression of the first law of thermodynamics for the system or for the surroundings. So here on the left-hand side, this is the first law of thermodynamics from the point of view of the system, where this is showing that the change in the internal energy of the system, du, is equal to these three contributions. So the contributions from the change of entropy, change in volume, and the change of the number of moles of various chemical species. Now we can write an analogous equation for the surroundings. On the right here, this is the first law of thermodynamics for the surroundings. And you can see that this equation is exactly the same as on the left, except that we're writing it in terms of the potentials of the surroundings and then the amount of different types of matter that are entering the surroundings. So this is the same thing, just written from the point of view of the surroundings. And the fact that these two equations are exactly the same format is a first clue that it really doesn't matter what you define as the system and what you define as the surroundings, that these two are really interchangeable with each other. But this has given rise to this modern statement of the first law of thermodynamics, which is also the subject of another video on my channel, just about the first law of thermodynamics, a modern interpretation, and also a paper with Dr. Chen and myself published in MRS Bulletin. But this description of the first law of thermodynamics, rather than writing it in terms of Q plus a W, heat transfer plus work, it gives a more intuitive understanding of the first law because this is written based on fundamental thermodynamic quantities, the three different potentials, temperature, pressure, and chemical potential, and then the exchange of three different types of matter, the entropy, the volume, and the number of species, N. This is also equally applicable to reversible and irreversible processes and applies to both open and closed systems. So we're going to be working with this modern statement of the first law to further demonstrate our points about the surroundings of the system. So let us consider now the combined first and second law applied to the system. So we just covered the first law. The second law of thermodynamics for the system can be written as shown here, where the change in entropy of the system is ds. And there are two contributions to that change of entropy. There is ds superscript E. The superscript E means the amount entering the system from the surroundings. So this term is the amount of entropy that is entering the system from the surroundings. And then we have to also consider that there may be internal irreversible processes happening within the system itself. And that adds this additional contribution here, ds superscript I, meaning internal, comma IR, meaning irreversible. So this second term here on the right-hand side is entropy created from irreversible processes that are internal to the system. So this has to be greater than or equal to zero. If it's zero, that means that everything is reversible. If this is greater than zero, then that means there are irreversible processes. Either way, this equation is valid. So it's equally applicable for both reversible and irreversible cases. And if you add these two together, that gives you the total change of entropy of the system. Now what we want to do is to combine the first and the second laws. So we're going to take our first law of thermodynamics from the previous slide, where we had a dSE here. And you can see from the second law of thermodynamics, the dSE is simply equal to ds minus ds irreversible. So what you see here in parentheses, this was dSE on the previous slide, and we are replacing that by this description from the second law of thermodynamics, ds minus ds from the irreversible internal processes. Everything else here remains the same. There are a couple of ways that we can represent this combined first and second law of thermodynamics. This upper line here shows an internal energy representation, where it's just simply taking the first law and replacing the ds entering the system with the expression from the second law. We can also write an entropic representation of the combined first and second law, and all that we need to do there is to solve for ds. So taking this equation and solving for ds, we get the equation down here at the bottom, where this is now the same equation, just written in terms of the change of entropy instead of the change of internal energy. These are both identical equations. They've just undergone algebraic manipulation to write it either in terms of the internal energy or in terms of the entropy. They're both equally valid. Now, that was the change of entropy of the system. Now let us consider what is happening with the entropy of the surroundings. So as I stated up front in this presentation, in the study of thermodynamics, the system, by definition, is the part of the universe that is of primary interest. We define the system to be whatever it is that we want to study. And for the system, we must account for both the influence of its surroundings and the processes within the system known as internal processes. Now, the difference is, since what we care about is the system, in contrast, internal processes within the surroundings are not of interest, since they do not have any direct influence on the system itself. So when we are treating the surroundings, we don't care about the irreversible processes happening in the surroundings. They may happen there, they may not happen there. We don't need to make any assumptions about reversibility of processes in the surroundings. The fact is that it just doesn't matter because it doesn't affect the system itself. So therefore, we can write the second law of thermodynamics for the surroundings as shown here on the lower left, where the change of entropy of the surroundings is simply equal to the entropy entering the surroundings from the system, because that's the part that we care about when we are focusing on our study of the system. Now, normally there would also be a contribution from any irreversible processes that may be happening in the surroundings. That may be there, that may not be there, but because we are focused on the system, these irreversible processes in the surroundings don't matter. And so this is taken to be zero, by which we mean that this contribution is simply ignored. Now what we can do is combine the first and second laws to the surroundings. So we've got the first law for the surroundings here. This is the change in the internal energy of the surroundings, having our three contributions here. So the three terms based on the potentials of the surroundings, the temperature, pressure, and chemical potential of the surroundings, and then the amount of the three types of matter entering the surroundings, the amount of entropy entering the surroundings, the amount of volume, and the amount of chemical species. Now, given this simplified second law from the previous slide, it's very simple to write a combined first and second law in this entropic interpretation for the surroundings itself. So this is simply solving for the change of the entropy of the surroundings. Now, one thing to note here, there are no requirements regarding the size of the surroundings. We never needed to make any assumption about the surroundings being large or small or anything. Also, the reversibility of internal processes within the surroundings are not relevant, so we didn't need to make any assumptions about whether they exist or not. And the reversibility of the exchange processes between the system and the surroundings. Also, we do not need to make any assumptions about them. So all of these assumptions that have been made in previous textbooks, they might be true or they might not be true, but the fact is that it really doesn't matter. That thermodynamics is equally valid whether or not those assumptions are true. Now, let's take a look at some of the interactions between the system and its surroundings. So regardless of the nature of the boundary between a system and its surroundings, from energy conservation, we know that the change of the internal energy of the system, here du, plus the change of the internal energy of the surroundings must equal zero because the energy of the universe is a constant, and so the du must equal minus du of the surroundings in order for the total energy of the universe to be conserved. So from that energy conservation, we can write the first law of thermodynamics for the system in terms of the internal energy change of its surroundings. So this is the du of the system. This must be equal to minus du of the surroundings, which means that we can take our description of the first law for the surroundings and just multiply it by -1, and that gives us the du. So this is now the internal energy of the system now being written in terms of what is changing from the perspective of the surroundings. These are both equally valid. Now, since mass is also conserved, that means that the dn of the system must equal the dn entering the system from the surroundings, and that must equal minus the dn of the surroundings. So any mass that leaves the surroundings and comes into the system, it's the total mass is conserved, so the flow in is equal to the minus flow out. One can also consider that if volume is also conserved, that the dV of the system would be equal to the dV of the volume entering the system from the surroundings, and that is simply minus dV of the surroundings if the total volume is also conserved. And under those assumptions, the first law for the system can then be written as du equals, we've got our entropy term here, but because of the dV of the surroundings is equal to minus dVE, we can just replace the dV of the surroundings with a minus dVE. And same thing here for the change of n in the surroundings. That's just minus the change of n going into the system. So this just flips the sign for these last two terms. These are all equivalent ways of writing the change of internal energy of the system. So some expressions here for the change in internal energy of the system. We've got the one that we just derived here on the top, and then our usual representation of the first law for the system shown as the second line. And we can write the change of the entropy entering into the system as being the minus of the change of entropy entering the surroundings, because They must be negative of each other, plus any irreversible processes that are happening. And so that is the summation of those two terms here. This left term, ds surroundings, includes both the amount of entropy exchanged through pure heat conduction and the amount of entropy carried by chemical matter. And the second part is the amount of entropy created during the exchange process between the system and its surroundings. Now, if we consider different ways of writing the entropy changes, the dSE, the amount of entropy entering the system, we can write this as minus ds of the surroundings plus ds of the irreversible exchange here. And so that would have all of these contributions shown here, where we've got the minus ds of the surroundings plus then these contributions to temperature difference between the surroundings and the system, pressure difference between the surroundings and the system, and chemical potential difference. The increase in the entropy of the system, ds as a whole, is dSE plus ds of the internal irreversible processes. And we can just add those together to include this extra term from the internal irreversible processes. And finally, we can also write the total entropy created in the universe, ds total, as the ds of the system plus the ds of the surroundings. And putting it all together, this gives us then the expression for how much the entropy of the universe is increasing as a result of the processes under study. And if you want to see, all the details of these derivations, feel free to check out our paper in MRS Bulletin. Next, I wanted to consider what if we have a thermodynamic system that consists of two subsystems, subsystem 1 and subsystem 2. And this is an isolated composite system. Subsystem 1 has temperature T1, subsystem 2 has temperature T2. And what we're going to assume is that these two subsystems are divided by a wall that is thermally conductive, so it allows the transfer of heat, but it is mechanically fixed and chemically impermeable. So what this means is that thermal matter can be exchanged. In other words, entropy can be exchanged between subsystems 1 and 2, but there is no change of mechanical matter, so there's no volume exchange, and there's no exchange of chemical matter. So what this means is that the ds1 is not equal to 0, so there can be entropy entering subsystem 1 from subsystem 2. Likewise, the ds2 is not equal to 0 because there could be entropy entering subsystem 2. But the change of volumes and the change of the number of moles of chemical species are 0 because this boundary is considered to be mechanically fixed and chemically impermeable. And because of those assumptions, in these cases, the change of the internal energy of subsystem 1 is just T1 times ds1. And the change of internal energy of subsystem 2 is du2 is equal to T2, the temperature of that second subsystem, times ds2. And of course, we know from the first law of thermodynamics that du1 plus du2 is equal to 0. So the total internal energy must be constant. Now, the reason that we're setting up this composite system with two subsystems is to show you that it is completely arbitrary which one of these you consider to be the system and which one is considered to be the surroundings. So let us consider case 1, where subsystem 1 is the system. If subsystem 1 is the system, then we consider subsystem 2 is the surroundings. And so in the system, in subsystem 1, we have a temperature T1. We have a change of entropy of subsystem 1, which is the entropy entering subsystem 1, plus the entropy contribution from any internal irreversible processes. Therefore, the change of internal energy is T1 times this ds1. And we've got ds1e, and the change of internal energy then is ds1 minus the ds1 of the internal irreversible processes. Now, for subsystem 2, the surroundings, Since we don't care about irreversible processes in the surroundings, we just have the contribution of the entropy change due to the entropy entering subsystem 2 from subsystem 1. So that gives us these expressions for ds2 and du2. And again, the first law must be valid. So what we can do is write then the change of the entropy in subsystem 1 as having these two contributions here, and the change of the entropy of subsystem 2 as having this single contribution. When we apply the first law, we know that du1 is equal to minus du2. So we can just substitute the du1 by a minus du2 or the du2 by a minus du1. That is just application of the first law. And then we can get the total entropy change of the composite system, ds total, by summing up the entropy changes of the two subsystems. So ds total is equal to ds1 plus ds2, and we just add these two terms together. And at the end, what we get is the first term, which is equal to this temperature difference between the surroundings and the system divided by the product of those two temperatures times du1 plus any irreversible contribution to the increase in entropy coming from internal processes within subsystem 1. Now, here we arbitrarily made the choice that subsystem 1 is the system and subsystem 2 is the surroundings. Case 2 is, what if we flip the assumption? What if we say that now the second subsystem is the system and the first subsystem is the surroundings? So now all that we have done here is just swapped the subscripts. So everything that had a subscript 1 now has a subscript 2. Everything that had a subscript 2 now has a subscript 1. We can write down the same equations for the entropy, apply the first law in exactly the same manner, and get an expression for the total change of entropy now where we've just swapped which is defined as the system versus the surroundings, and you get the same result. And so this is showing that it is arbitrary. What you choose as the system versus the surroundings is arbitrary. You can assume either way, and all the equations that you derive are equally valid. So to conclude this presentation, the choice of system versus surroundings is arbitrary, since the system and the surroundings are interchangeable. Secondly, the surroundings do not need to be large. They do not need to be any particular size. It doesn't matter. Next, the surroundings do not need to be isothermal. They do not need to be isochoric or constant volume. And lastly, there's no need to assume that processes involving the surroundings are reversible. So a lot of these assumptions that have been made in previous textbooks are really unnecessary assumptions. These are not needed in order to work out classical thermodynamics. I hope you enjoyed the presentation. There is quite a bit more in our paper. So if you're interested in learning more, please check out the paper, check out Dr. Chen's textbook, and you are always more than welcome to leave questions or comments down below. Thank you very much, everyone. Hope you have a great day.